Module 3, Lecture B, Metrics and Errors. By the end of this lecture, you will be able to calculate mean squared error for regression predictions using manual code, compute confusion matrix, accuracy, precision, recall, and F1 score for classification tasks, and explain overfitting and underfitting using training and testing performance patterns. Regression error metrics, regression residuals. Regression residuals are the differences between actual numerical outcomes and a model's predictions. They show how much the model overestimated or underestimated each case, such as a house price prediction. Studying residuals helps identify specific prediction errors and supports the creation of accurate regression error metrics. Residuals show how far predictions are from actual values and whether the model is overpredicting or underpredicting. By examining residual patterns, such as errors in electricity demand forecasts or student score predictions, we can spot systematic problems that overall error measures may hide. This helps improve models for particular groups or conditions. When evaluating a regression model, first examine the residuals before relying on summary metrics like mean squared error. Small, randomly scattered residuals suggest the model captures the main pattern, while growing errors, clusters, or consistent bias can reveal missing features, outliers, or weak performance in certain cases. Residual analysis shows where predictions work well and where the model needs improvement. Python code. Regression residuals. Residuals show the difference between actual and predicted values. Their direction indicates whether a model is overpredicting or underpredicting, helping engineers quickly inspect prediction errors. The actual bridge deflections are stored as millimeter measurements in a list. These values represent observed deflection under specific conditions and will be compared with predicted values to evaluate prediction accuracy. The predicted bridge deflections are stored as millimeter values from a model or calculation. These predictions will be compared with actual measurements to find residuals and assess how accurate the predictions are. The code first checks that the actual and predicted bridge deflection lists have the same length, so each actual value can be paired with a prediction. If they differ, it raises an error and stops the residual calculation. This validation helps prevent mismatched data from causing incorrect results. To evaluate prediction errors, create a list of residuals by comparing each actual deflection with its predicted value. Pair the two sets of values, subtract each prediction from the corresponding actual measurement, and store the result. These residuals show how far each prediction is from the observed data. The process labels each residual to describe the prediction error. A positive residual means the model underpredicted, a negative residual means it overpredicted, and a zero residual means the prediction was exact. These labels make the residuals easier to interpret in terms of prediction accuracy. The code creates a residual table with columns for the case number, actual value, predicted value, residual, and direction. It loops through the related values together using a 1-based index as the case number, then prints each row in a consistent format. Values are rounded to 1 decimal place, and the residual includes a positive or negative sign to make overpredictions and underpredictions easy to identify. The average signed residual is found by averaging all residual values into one number. This shows the typical direction of prediction error, indicating whether predictions tend to be above or below the actual values. Reporting it with 2 decimal places and a positive or negative sign makes the overall bias easy to interpret. This script compares actual and predicted bridge deflections by first confirming the two datasets match in length. It calculates each residual as the actual value minus the predicted value, then identifies whether the prediction was too low, too high, or exact. It reports these results for each case and computes the mean residual to summarize the average prediction error and reveal any overall bias. Mean squared error. Mean squared error measures how close a regression model's predictions are to the actual values. It squares each prediction error and averages the results into one overall score. A lower mean squared error means the model's predictions are closer to the truth, while a higher value means the model is making larger mistakes. Squaring errors in mean squared error prevents positive and negative mistakes from canceling each other out. It also gives extra weight to large errors, making the measure especially useful when big prediction mistakes are costly, such as in staffing or perishable goods forecasting. As a result, mean squared error reflects average error while strongly penalizing predictions that are far from the actual values. Mean squared error is found by comparing each prediction with the actual value, squaring the differences, and averaging them. Calculating it manually helps clarify that it measures prediction error, with larger mistakes penalized more strongly. Although the result is in squared units, it is useful for comparing models on the same dataset, where a lower value usually means better predictions. Python code. Mean squared error. Manual metrics help reveal where a model makes errors. Squared residuals are especially useful because they give more weight to large mistakes. Simple civil engineering examples can make these errors easier to interpret. We define a list of actual concrete strengths measured in megapascals. These observed values provide the reference for comparing model predictions and calculating measures such as residuals and errors. A list of predicted concrete strengths in megapascals is created, so the predictions can be compared with the actual values. This comparison allows residuals and squared errors to be calculated, which are then used to find the mean squared error and assess prediction accuracy. Before calculating residuals, the code checks that the actual and predicted strength lists have the same length. This ensures every prediction matches one actual value. If the lengths differ, it raises an error and stops the calculation. First, the analysis checks whether any actual concrete strength observations are available. If none are provided, it raises an error because at least one observation is required before calculating metrics. To measure prediction errors, create a list to store residuals, then compare each actual value with its predicted value. For each pair, subtract the prediction from the actual observation and save the result. These residuals show how far each prediction is from the true value. To prepare for mean squared error, each residual is squared and stored in a list of squared errors. Squaring makes all errors positive and gives larger residuals more influence, helping measure how far the predictions are from the actual values. Mean squared error is found by adding all the squared differences between actual and predicted values, then dividing by the number of observations. It represents the average squared error, so a lower value means the predictions are closer to the actual results. The output compares actual concrete strengths with the model's predicted strengths, then shows the residuals, or prediction errors. Squaring these errors highlights larger mistakes, and their average gives the mean squared error in megapascals squared. A lower mean squared error means the regression model's predictions are closer to the actual values and the model is performing better. This script measures prediction accuracy for concrete strength using mean squared error. It first confirms that the actual and predicted values are valid, then finds the differences between them, squares those errors, and averages the results. The output shows the key values and the final mean squared error rounded to 2 decimal places. A lower value means the predictions are closer to the actual strengths, and the model is performing better. Error calculation. In regression, error is measured by comparing each prediction with the actual value and finding the difference called the residual. A model is evaluated by looking at the pattern of these residuals across many observations, not just a single case. Summarizing these differences shows how well the model performs overall. Mean squared error is found by squaring each prediction error and then averaging the results. Squaring prevents positive and negative errors from canceling out, and it gives larger mistakes more weight. The final average shows both how often the model is wrong and how serious those errors are. Manual error calculation shows how automated metrics evaluate a model. For mean squared error, you compare each prediction with the actual value, square the differences, and average them. A lower value means predictions are closer to reality, while a higher value signals larger or more frequent mistakes. The size of the error should always be judged in the context of the real-world decision it supports. Python code. Error calculation. Regression model quality can be judged by its prediction errors. Squaring the errors keeps positive and negative residuals from canceling out, and the mean squared error gives a single summary of how large the model's mistakes are. We store the actual concrete strengths, measured in megapascals, as the true values for each sample. These values will be compared with the model's predictions to calculate prediction errors. The predicted concrete strengths are stored as a list of model outputs in megapascals. These predictions can then be compared with the actual strengths to calculate errors and evaluate how accurately the model performs. The code first verifies that the actual and predicted strength lists have the same length, so each actual value matches a prediction. If they do not match, it raises an error explaining that the lists must be equal in length. This check helps ensure consistent data before calculating errors. First, the code checks whether the list of actual strengths is empty. If it is, it raises an error because at least one prediction is needed before calculations can continue. This helps ensure the later steps have valid data and prevents avoidable failures. To evaluate prediction accuracy, we collect residuals, which are the differences between predicted and actual strengths. Each predicted value is paired with its actual value, and the actual strength is subtracted from the prediction. These residuals show how far each prediction is from the true value. Create a list to store the squared residual errors, then square each error and add it to that list. Squaring makes every error positive, removing direction, and preparing the values for metrics such as mean squared error. Mean squared error is found by adding all the squared errors, counting how many predictions were made, and dividing the total by that count. The result is the average squared error, which summarizes prediction accuracy. Lower values indicate better model performance. The output compares actual concrete strengths with the model's predicted strengths, then shows the residual errors between them. These errors are squared, so positive and negative differences do not cancel out. The mean squared error is then calculated as the average squared error rounded to 2 decimal places, giving one overall measure of prediction accuracy. A lower value means the model's predictions are closer to the actual strengths. This script measures prediction accuracy for concrete strength using mean squared error. It first confirms that the actual and predicted strength lists are valid, then finds the differences between predicted and actual values, squares them, and averages the results. It reports the key values and the final error rounded to 2 decimal places, where a lower mean squared error means the predictions are closer to the actual strengths. Classification metrics. Confusion matrix. A confusion matrix summarizes how a classification model's predictions compare with the true labels. For binary classification, it separates results into true positives, true negatives, false positives, and false negatives. This helps show not just overall accuracy, but where the model is making correct decisions or specific types of mistakes. A confusion matrix helps show what kinds of mistakes a classification model makes and whether those mistakes are acceptable in context. For example, in medical screening or fraud detection, false positives and false negatives can have very different consequences. By examining these errors, you can decide whether the model needs adjustment. The confusion matrix also provides the basis for key performance measures such as accuracy, precision, recall, and F1 score. Confusion matrices are useful for both binary and multi-class classification. They show which categories a model confuses, such as mixing account questions with billing issues, giving more detail than accuracy alone. This helps identify where the model needs improvement, such as better training data or clearer class definitions. Python code, confusion matrix. This script shows how to build classification metrics by hand and use confusion matrices to understand different kinds of prediction errors. Civil inspection labels provide a concrete context for interpreting the results. This script imports 3 key Python libraries for data analysis and visualization. Pandas handles tabular data. Seaborn creates clear statistical graphics, and Matplotlib PyPlot supports building visualizations. Together, they provide the tools needed to create and display the confusion matrix and related metrics. We start with a list of the true bridge inspection results, where each bridge is labeled as either safe or unsafe. These actual labels provide the ground truth needed to compare against model predictions and evaluate classification performance. The code creates a list of model predictions for bridge inspections, marking each bridge as safe or unsafe. These predicted labels are later compared with the actual labels to evaluate performance using measures such as accuracy and precision. Before building a confusion matrix, first confirm that the actual labels and predicted labels have the same length. This ensures every prediction matches one true label and prevents incorrect counts. An assertion can perform this check automatically and stop the program if the data is mismatched. For this classification task, the positive class is unsafe because it is the condition we want to detect. The negative class is safe, meaning the condition is absent. Defining these labels clearly is important for metrics such as true positives and false negatives. A confusion matrix can be counted by comparing each actual label with its prediction. True positives are unsafe cases predicted as unsafe, and true negatives are safe cases predicted as safe. False positives are safe cases predicted as unsafe, while false negatives are unsafe cases predicted as safe. These 4 counts summarize how well the model is classifying safe and unsafe examples. To evaluate a classification model, first find the total number of predictions by combining correct and incorrect results. Accuracy is the share of all predictions that were correct, using both true positives and true negatives. Precision shows how many predicted positives were actually positive, while recall shows how well the model found the real positive cases. Each calculation should account for possible zero totals to avoid division errors. The F1 score combines precision and recall into one balanced measure. It is calculated as 2 times precision times recall divided by their sum, so it accounts for both false positives and false negatives. If precision and recall add up to 0, the F1 score is set to 0 to avoid division by 0. The output summarizes a classification model's performance by showing the counts of correct and incorrect predictions, including true positives, true negatives, false positives, and false negatives. It then reports accuracy, precision, recall, and the F1 score, each rounded to 2 decimal places. Together, these metrics give a quick view of how well the model predicts overall and how effectively it handles positive cases. A confusion matrix can be organized in pandas as a 2-dimensional data frame that compares actual classes with predicted classes. Its rows represent the actual safe and unsafe outcomes, while its columns represent the predicted safe and unsafe outcomes. The 4 entries show true negatives, false positives, false negatives, and true positives, making it easy to assess how well the classification model performed. This code creates a clear heat map of a confusion matrix for bridge safety classification. It sets up the plot, displays the matrix values as integers, uses a blue color scheme, and removes the color bar for a cleaner look. The plot is titled and labeled, so the true labels and predicted labels are easy to identify. Then the layout is adjusted and the figure is displayed. This script evaluates a bridge safety classifier by comparing actual inspection results with predicted safe or unsafe labels. It builds a confusion matrix to count correct and incorrect predictions, then calculates accuracy, precision, recall, and the F1 score. It also displays the confusion matrix as a heat map, helping summarize where the model performs well and where it makes errors. Precision. Precision measures how often a model's positive predictions are actually correct. It is especially important when false alarms are costly, such as when a spam filter wrongly sends important emails to the spam folder. In short, precision tells us how trustworthy the model's positive claims are. Precision in binary classification tells us how reliable a model's positive predictions are. It compares correct positive predictions with all positive predictions, including false alarms. High precision means the model produces few false positives, so when it labels a case as positive, it is usually right. In medical screening, this means flagged patients are likely to have the condition, though precision alone does not show whether every true case was found. Precision measures how often a model's positive predictions are actually correct. A model can have high precision by predicting positives only when it is very confident, which reduces false positives, but may miss harder cases. Because of this, precision alone does not fully describe model quality. It is most useful when false positives are costly, such as in fraud detection or plagiarism checks. Python code, precision. Precision shows how reliable a model's positive predictions are. In classification, false positives lower precision, such as when bridge inspection labels incorrectly mark a case as positive. We define a list of true bridge defect labels, where 1 means a defect is present and 0 means it is not. These labels provide the ground truth for comparing against predictions and measuring accuracy. Predicted bridge defect labels are represented as binary values, where 1 means a defect is predicted, and 0 means no defect is predicted. These predictions are then compared with the actual labels to measure prediction accuracy. First, check that the actual and predicted label lists are the same length. This ensures each prediction can be matched to the correct actual label for accurate comparison. If the lengths differ, the data is mismatched, and later calculations may be incorrect. True positives are counted by comparing each actual label with its predicted label. For each pair, the count increases only when both labels indicate a defect. This gives the number of cases where the model correctly predicted a defect that was truly present. This code counts false positive predictions by comparing each actual label with its predicted label. It adds 1 whenever the actual label is 0 but the prediction is 1, giving the total number of false positives in the dataset. Precision measures how often a model's positive predictions are correct. To find it, first count all positive predictions by combining true positives and false positives. Then divide the true positives by that total. If the model made no positive predictions, precision is set to 0 to avoid dividing by 0. The output summarizes precision by showing true positives, false positives, and the total number of predicted defects. It then reports precision to 2 decimal places, indicating the share of predicted defects that were actually correct. In short, precision tells us how reliable the model's defect predictions are. This script measures a classification model's precision for bridge defect detection by comparing actual labels with predicted labels. It counts true positives where a defect is correctly predicted, and false positives where a defect is predicted but not actually present. Precision is the share of positive predictions that were correct, helping show how reliable the model is when it predicts a defect. F1 score. The F1 score combines precision and recall into one measure, making it useful when classes are imbalanced or when the positive class matters most. Unlike accuracy, it can reveal when a model seems successful overall but misses important positive cases. A high F1 score means the model both identifies positives carefully and captures most of the true positives. The F1 score summarizes the balance between precision and recall. Precision shows how often positive predictions are correct, while recall shows how many real positives are found. In a spam filter, this means balancing catching spam with avoiding marking important emails as spam. A high F1 score rewards models that perform well on both measures. The F1 score is useful when both false positives and false negatives matter, such as in fraud detection. False alarms can frustrate customers, while missed fraud can cause financial loss. By combining precision and recall, the F1 score helps analysts think about this trade-off, but it should be used alongside other metrics rather than as the only measure of model performance. Python code, F1 score. This example shows how to compute the F1 score for classification by combining precision and recall into one balanced measure. It can be done directly without using a machine learning library. We define a list of true bridge inspection results, where each value shows whether a bridge is damaged or undamaged. These actual labels will later be compared with predicted labels to measure prediction accuracy. The model's bridge inspection predictions are stored as binary labels, where 1 means damage is predicted and 0 means no damage is predicted. These predicted labels are later compared with the true labels to measure model performance. First, confirm that the actual and predicted label lists are the same length, since each prediction must match one actual label. An assertion enforces this check and stops the process if the counts differ. This prevents misaligned comparisons before any further calculations are made. True positives are the cases where a bridge is actually damaged, and the model also predicts it as damaged. To calculate them, we compare each actual label with its predicted label and count the pairs where both indicate damage. Adding these counts gives the total number of correctly identified damaged bridges. To count false positives in bridge inspection predictions, compare each actual label with its predicted label. A false positive occurs when the actual label shows no damage, but the prediction indicates damage. The total false positives are found by counting all cases where this mismatch occurs. False negatives are counted by comparing each actual label with its predicted label. A false negative occurs when the bridge is actually damaged, marked as 1, but the model predicts no damage, marked as 0. Adding up these cases gives the total number of damaged bridges the model failed to identify. True negatives for undamaged bridges are counted by comparing each actual label with its predicted label. When both labels are 0, the bridge was correctly identified as undamaged, so it adds 1 to the total. Summing these matches gives the total number of true negatives in the dataset. Precision measures how accurate the positive predictions are. It is found by dividing true positives by the total number of positive predictions, including both true positives and false positives. If there are no positive predictions, precision is set to 0 to avoid a division error. Recall measures the share of actual positive cases that were correctly identified. It is calculated by dividing true positives by the total of true positives and false negatives. To avoid division by 0, the calculation sets recall to 0 when that total is 0, making the result safe and reliable. The F1 score combines precision and recall into one balanced measure of classification performance. It is calculated by taking 2 times precision times recall, then dividing by the sum of precision and recall. If that sum is 0, the F1 score is set to 0 to avoid a division error. A confusion matrix summary shows the counts of true positives, false negatives, and true negatives. These values give a quick view of how many predictions the model got right or wrong in each category. The format method places the calculated counts into a readable message. Precision and recall are printed as rounded decimal values with 2 places. This gives a quick, clear summary of a classification model's performance using 2 key evaluation metrics. Finally, we display the F1 score, which summarizes model performance by balancing precision and recall. Formatting it to 2 decimal places makes the result clear and easy to read. This script evaluates a binary bridge inspection classifier by first checking that the actual and predicted labels have the same length. It counts correct and incorrect predictions for damaged and undamaged bridges, then uses those counts to calculate precision, recall, and the F1 score. Finally, it reports the confusion matrix and these 3 performance measures, giving a compact summary of how well the model identifies bridge damage. Generalization issues. Underfitting patterns. Underfitting occurs when a model is too simple to learn the main patterns in the data, so it performs poorly on both training and new examples. Low scores on both sets usually show that the model has not captured the underlying relationships. For example, predicting house prices using only the number of bedrooms ignores important factors, leading to inaccurate results. Underfitting occurs when a model performs poorly on both training and testing data, even if the gap between them is small. This can look like good generalization, but it really means the model has not learned enough to solve the problem. For example, a medical risk model based only on age may be consistent across datasets, but still not clinically useful. This is a sign of high bias, where the model is too simple for the task. Underfitting occurs when a model is too simple or too constrained to learn the training data well. This can result from too few features, excessive regularization, limited training, or lost information during preprocessing. To fix it, increase the model's learning capacity by improving features or data quality, using a more flexible algorithm, reducing constraints, or training longer. Python code, underfitting patterns. This script shows underfitting, where both training and test errors remain high because the model is too simple to capture the curved pattern in the data. We import NumPy to handle arrays and numerical calculations efficiently. We also import Matplotlib's plotting tools to visualize data and model predictions, helping us assess performance. We create reproducible sample data for a civil engineering beam scenario by using a fixed random seed. Then we define 40 evenly spaced measurement positions from 0 to 10 along the beam. We add normally distributed random noise to the data to simulate measurement variability. The underlying settlement pattern is nonlinear, combining a constant term, a linear term in x, and a squared term in x. Together, the curve and noise create a more realistic dataset where the true relationship is not simply a straight line. The data is split into training and testing sets based on the x values. Values up to 7 are used for training, while values greater than 7 are held out for testing. This lets us check how well the model performs on data it has not seen before. Before fitting the model, the code verifies that both the training and testing sets contain more than 5 data points. This helps prevent modeling with too little data and supports a more reliable evaluation. A simple constant model predicts the same value for every training example. To fit it, we use the average target value from the training data as the constant prediction. Then assign that value to all training predictions. This creates a flat, very basic model that ignores variation in the data. We create a simple baseline by predicting the same constant value for every test example, using the average target value from the training data. We also collect the true target values for both the training and test sets. These true values will be used to compare against the predictions and evaluate performance. We evaluate the model by calculating mean squared error on both the training and testing data. This means averaging the squared differences between the true values and the model's predictions. Comparing these two errors shows how well the model fits each dataset and can help reveal underfitting. The model's training and testing mean squared errors are compared by calculating their absolute difference, called the error gap. The training error shows how well the model fits the training data, while the testing error shows how it performs on unseen data. If both errors are high, the model is likely underfitting, meaning it is too simple to capture the main patterns in the data. Set up a plotting area, then show the training and testing data as separate scatter plots on the same graph. Labeling each group makes it easier to compare the actual measurements from both datasets visually. The plot uses a red horizontal line to show the constant prediction from an overly simple model, labeled as the too simple model. The axes identify the beam position in meters and the measured settlement in millimeters, making the load test results easier to interpret. The plot is finalized by adding a clear title that highlights underfitting, where the model performs poorly on both training and testing data. A legend identifies the data and prediction. The layout is adjusted so everything fits neatly, and the plot is displayed to help assess the underfitting pattern visually. This example shows underfitting by using a constant model to predict a nonlinear settlement curve. The model simply predicts the average training value, so it cannot follow the curved pattern in the data. As a result, both training and testing errors are high, with only a small gap between them. This indicates the model is too simple and performs poorly on both datasets. Overfitting patterns. Overfitting occurs when a model learns the training data too closely including noise or irrelevant details, instead of learning general patterns. It may perform very well on training data, but poorly on new testing data. The key warning sign is a large gap between training and testing performance, with training results much better than testing results. As models become more complex, they are more likely to overfit by learning noise, outliers, or rare quirks in the training data instead of stable patterns. This can make training accuracy look high, while real-world performance is poor. A useful model must generalize beyond memorized details to capture signals that hold across new data. Overfitting can be detected by comparing model performance on training and testing data over time. If training error keeps falling while test performance stops improving or gets worse, the model is likely learning noise instead of patterns that generalize. In classification, this may appear as rising training accuracy or F1 score, while test results stay flat or decline, which can lead to poor performance on new real-world cases. Python code, overfitting patterns. Compare training and testing errors to detect overfitting. In simple polynomial fitting, overfitting appears when the model performs much better on training data than on testing data, creating a widening performance gap. The script imports NumPy for efficient numerical work with arrays and Matplotlib pyplot for creating plots. Together, these libraries provide the basic tools for data manipulation and visualization. To make synthetic data repeatable in civil engineering simulations, initialize NumPy's default random number generator with a fixed seed, such as 7. This ensures the same random values are produced each time the code runs, supporting reproducible experiments and simulations. We generate simple training data by creating 12 evenly spaced input values from 0 to 10 to represent traffic volume. The output represents bridge vibration based on a linear pattern where each input is scaled by 0.7 and increased by 2. Random noise with mean 0 and standard deviation 1.2 is added to make the data more realistic. We create 12 evenly spaced test points between 0.5 and 9.5 to represent unseen data. For each point, we generate a matching y value using the same linear pattern as the training data, where y equals 2 plus 0.7 times x. Then add random noise with mean 0 and standard deviation 1.2. This keeps the test data generation consistent with the training process. Check that each training input has a matching training output, and then each testing input has a matching testing output. This consistency is essential for correct learning and reliable evaluation, because predictions must be compared against the right actual values. We compare model complexity using polynomial degrees 1, 3, and 10. For each degree, we will record the mean squared error on both the training and testing data, so we can see how performance changes as the model becomes more complex. For each chosen polynomial degree, we fit a model to the training data by finding the best polynomial coefficients. We then turn those coefficients into a polynomial object, making it easy to evaluate the model on new inputs. This prepares the model for prediction and performance assessment. The polynomial model is used to make predictions on both the training data and the testing data. Comparing these results shows how well the model performs on data it has seen versus new data. A large difference between the two can indicate overfitting. We evaluate the model by calculating mean squared error on both the training and testing data. For each set, we compare the actual values with the model's predictions, square the differences, and average them. The training error shows how well the model fits the data it learned from. while the testing error shows how well it performs on unseen data. The code records the training and testing mean squared errors for each polynomial degree. Tracking both values shows how well the model fits the training data and how well it performs on unseen data. Comparing them helps reveal overfitting when training error is low but testing error is high. The code prints a compact comparison of polynomial degree, training error, and testing error. It pairs each degree with its corresponding errors and displays them in a formatted line. This makes it easy to see how increasing model complexity affects performance, including the overfitting pattern where training error stays low while testing error rises. Overfitting occurs when a model has low error on training data but higher error on testing data. This means it performs well on examples it has already seen, but struggles with new data because it has learned noise instead of the underlying pattern. Create a plot that compares training and testing mean squared error across polynomial degrees. The training errors are shown with circular markers and the testing errors with square markers, making it easy to see how error changes as model complexity increases. This comparison helps reveal patterns such as overfitting. The plot is labeled to show how model complexity relates to prediction error. The x-axis represents polynomial degree, and the y-axis represents mean squared error. A clear title identifies the comparison between training and testing error, while the legend helps distinguish the two lines and makes the overfitting pattern easier to interpret. To finish the visualization, we add a lightly transparent grid to make the data easier to read without cluttering the plot. We then adjust the layout so all plot elements fit cleanly and display the final chart to show how model complexity relates to error rates. This example shows overfitting by fitting polynomial models of increasing complexity to synthetic civil engineering data relating traffic volume to bridge vibration response. As the polynomial degree rises, the model fits the training data better, so training error decreases. However, testing error increases, meaning the model performs worse on unseen data. The widening gap between training and testing error illustrates the trade-off between model complexity and generalization. Testing performance. Test performance shows how well a machine learning model is likely to handle new data. Strong training results alone can be misleading because the model has already seen those examples. A separate test set uses unseen cases to check whether the model has learned patterns that generalize. If test results are strong and close to training results, the model is more likely to perform well on future inputs, such as new apartment listings. Comparing training and testing performance helps identify underfitting and overfitting. If both results are poor, the model may be too simple or missing important predictors. If training performance is strong but testing performance is weak, the model may be overfitting by learning quirks in the training data that do not generalize to new cases. When judging test performance, consider both the gap between training and testing results and how well the model actually performs on test data. A small gap can still mean underfitting if both scores are low, while a large gap may be acceptable if test performance meets the needs of the application. The required standard depends on the use case, so use test results to decide whether the model is ready for deployment or needs changes such as simpler design or better data. Python code. Testing performance. Testing performance shows how well a model generalizes beyond its training data. Training results alone can be misleading, so compare training and testing performance to spot gaps and diagnose whether the model is fitting appropriately. We import NumPy for efficient numerical work with arrays and mathematical operations. We also import Matplotlib's plotting tools to create visualizations of data and model performance. A random seed is set to 7, so the generated values can be reproduced. Then, 24 evenly spaced property sizes from 500 to 2,500 square feet are created, forming the area data for a small civil engineering dataset. To make the rental price data more realistic, we add random noise drawn from a normal distribution with mean 0 and a standard deviation of 120. Rent is then calculated from a base price of $900 plus $1.15 for each square foot of area, with the noise added to reflect real-world variation. We use the first 16 area values as training inputs, representing listing square footage, and the first 16 rent values as training outputs, representing rental prices. This gives the model a subset of the data to learn from, while leaving other data available for later testing. To prepare the test data, we use the later listings by taking the square footage and matching rental prices starting from the 17th item. Keeping these examples separate from the training data lets us check how well the model performs on data it has not seen before. Before training or evaluating the model, we check that each dataset has matching inputs and labels. The training examples must align with the training rent values, and the testing examples must align with the testing rent values. These checks help catch data partitioning errors early and prevent mismatches during model training or evaluation. We compare polynomial models with degrees 1, 3, and 12 to represent increasing complexity. These are labeled as underfit, balanced, and overfit, showing the difference between a model that is too simple, one that fits appropriately, and one that is too complex. We create 2 empty lists to store root mean square error values for the training and testing data. Tracking these errors lets us compare model performance on both datasets and judge how well each model generalizes. The root mean square error helper function compares actual values with predicted values to measure model accuracy. It finds the average of the squared prediction errors, then takes the square root to return one overall error value. A lower value means the model's predictions are closer to the actual results. For each chosen polynomial degree, we fit a model to the training data using the area in square feet to predict rental price. The fitting process finds the coefficients that best match the data, then turns them into a polynomial function that can make predictions. This prepares the model to be evaluated on both the training and testing datasets. The model predicts rental prices for both the training and testing areas. These predicted values can then be compared with the actual rental prices to evaluate how well the model performs. The code records the root mean square error for both training and test predictions. Training error shows how well the model fits the data it learned from, while test error shows how well it performs on unseen data. Tracking both helps compare model performance across different levels of complexity. The code prints a diagnostic summary comparing model complexity with training and testing root mean square errors. It pairs each model label with its training and testing results, then prints them in a consistent format. This makes it easy to see how each model performs and how well it generalizes to new data. Create a plot to compare training and testing RMSE across the models. After setting up the figure, plot both RMSE series against the model labels with clear point markers and labels for the legend. This makes it easy to see how each model performs on training data versus testing data and how well it generalizes. The plot is labeled to show rental price error in dollars given a title that emphasizes model generalization issues, and given a legend to separate training and testing performance. These additions make the chart easier to understand and interpret. To finish the plot, we turn on a light, semi-transparent grid to make the data easier to read without cluttering the view. We then apply a tight layout so the plot elements fit cleanly without overlapping. Finally, we display the plot to review the model's training and testing performance. This script compares polynomial models for predicting rental prices from area using training and testing data. It measures performance with root mean square error on both sets. The linear model underfits, the 12th degree model overfits, and the cubic model gives the best balance between fit and generalization. The results show how increasing model complexity can improve performance up to a point, then make testing accuracy worse. In this lecture, you learned to calculate mean squared error for regression predictions using manual code, compute confusion matrix, accuracy, precision, recall, and F1 score for classification tasks, and explain overfitting and underfitting using training and testing performance patterns. In the next module, Module 4, we will go over none. Thank you for your attention. See you all in the next lecture.